Hello and welcome to Doc Plays Chemistry Lessons. Today we're going to be looking at nucleophilic addition elimination reactions. By the end of this lesson then, you should be able to do the following things. You should be able to apply IUPAC rules for naming acyl chlorides and acid anhydrides. Be able to draw the nucleophilic addition elimination mechanisms with acyl chlorides and acid anhydrides. Identify the products of reaction from acyl chlorides or acid anhydrides with alcohols, water, amines and ammonia. And finally, be able to recall the reaction conditions for reactions with acyl chlorides and also acid anhydrides. We've looked then at the acyl group in previous lectures, and we've seen how changing X can have different effects on our acyl group, the carbon double bond oxygen. Now, the nucleophilic addition elimination reaction, we're going to end up observing overall the replacement of the X group with another species Y. And we're going to look at how this reaction is done now. We're going to start off then with our acyl group, which has got an R carbon double bond oxygen and an X group here, where our X we're going to look at in a few minutes time to see what that can be. But importantly, it can either be a chlorine or it can be an O C double bond OR. If it's a chlorine, then it's an acyl chloride, and if it's the O C double bond OR, then it's an acid anhydride. In this reaction then, we're going to have a nucleophile which has got a hydrogen attached to it, and we'll look more specifically at these nucleophiles in due course. Importantly, our nucleophile has got a lone pair of electrons. As we've observed before, because we got a delta positive and a delta negative, we got a polar bond between the carbon and the oxygen. This lone pair of electrons is going to attack the carbon, and then from the double bonded oxygen, the pair of electrons go from the bond onto the oxygen. This leaves us once again then with a tetrahedral intermediate, where we now have a nucleophile attached to the carbon, which has also got a hydrogen on, and because the nucleophile didn't have a positive charge to start with, or a negative charge, it's donated its electrons, and therefore we have a positive charge. You'll notice we've now got a negative charge on the oxygen and a lone pair of electrons. This first step then is the addition reaction, and in the second step we now see the elimination. So the lone pair of electrons on the oxygen goes back in to reform a carbon double bond oxygen bond, and the bond between the carbon and the X group here goes towards the X group. This second step is called an elimination reaction because we have the loss of X minus. What we now have is an almost complete product with a newly attached nucleophile, but this nucleophile has got a positive charge, and to lose that positive charge, the hydrogen atom that's attached to the nucleophile donates the electrons from within the bond onto the nucleophile. What we're now left with then is that R group, the nucleophile attached with a neutral species. We have a hydrogen ion and the leaving group X minus that we saw before. Overall, what we've seen is something that looks a bit like a substitution reaction that we saw from our Year 1 A Level Chemistry course, where the X group on the carbon there is replaced with a nucleophile. However, because it's done in a two-step intermediate process, we actually have the addition of the nucleophile first, followed by the elimination, and therefore it's called an nucleophilic addition-elimination reaction. In your exams, you're going to need to be able to identify that reaction mechanism and also be able to draw that reaction mechanism, including any curly arrows, but you'll be given real molecules and real nucleophiles, and we're going to go and have a look at those possibilities that they could come up with now. So previously we've just seen that the RC double bond OX can have a nucleophilic addition elimination reaction, and there's two examples, either with an acyl chloride or an acid anhydride. So our acyl chloride occurs if we have RC double bond O and a chlorine. The suffix here for naming these is an oil chloride. So we have things like ethanoyl chloride, butanoyl chloride, and so on. This is the most reactive of our two examples because the chlorine atom here is electron withdrawing, making the carbon double bond oxygen even more polar because of the electron withdrawing capabilities of the chlorine atom, and therefore it's more susceptible to nucleophilic attack. The acid anhydride, on the other hand, is observed here where X is replaced by an OC double bond O R dash group. This is named by the suffix anhydride and also the respective carboxylic acid, so oic anhydride. Now, if R and R dash are equivalent, so let's say they're both 2 carbons in length, then the naming is just simply given by the name of the carboxylic acid. For example, if they're both 2 carbons, it would be ethanoic anhydride. However, if R and R dash are different, i.e. they're different carbon chain lengths, then we name each carboxylic acid. So if we had here a 2 carbon chain and a 3 carbon chain, we simply name them by the number of carbon chains. So it would be ethanoic if it was 2 carbons in the chain, propanoic anhydride. Here we would have a 3 carbon chain carboxylic acid and a 2 carbon chain carboxylic acid on either side here. And that's how we name our unsymmetrical acid anhydrides. We're now going to have a quick look at the individual reactions for the acyl chlorides and the acid anhydrides, and then look at all possible reactants and products. In each of these reactions then, we're going to be looking at possible nucleophiles that could react. And our possible nucleophiles that we're going to be using here are water, H2O. We could have an alcohol, which is going to be ROH. We can have ammonia, NH3, and we can also have an amine, and that can be either a secondary, primary, or tertiary amine. We're going to use our example here with our acyl chloride to look at the nucleophilic addition elimination reaction. We're going to look here at our 1,2 carbon chain length acyl chloride. So this is ethanoyl chloride. And we're going to look at the reaction in the first instance with water. So water is a hydrogen with, an oxygen with 2 hydrogen atoms and a lone pair of electrons, 2 for the oxygen. And as we saw for the general mechanism here, is going to attack the delta positive carbon, and then from the bonds between the carbon double bond oxygen, the double bond goes on to the oxygen there. What we form then is an intermediate, and remember here our intermediate now has the hydrogen and oxygens attached from the water, and we have a positive charge here on our oxygen. The lone pair of electrons then from the oxygen go back into the bond between the carbon and the oxygen, and between the carbon and the chlorine we lose the chlorine atom, and we're left there then with the water with a positive charge, and this hydrogen ion or atom then goes on to the oxygen, and we're left with an OH attached to that carbon. We also have the leaving groups of hydrogen ion and also our Cl-, which in this case form hydrogen chloride gas. And our product here is the carboxylic acid with 2 carbons in the chain, which is called ethanoic acid. Now, we said before that we could have one of 4 possible nucleophiles. We could have water, we could have an alcohol, we could have an ammonia, or an amine react. Now, in each of these cases, the chlorine carbon bond is the one that breaks, and that would react with the water to form hydrogen chloride gas, and a new bond would form from the lone pair of electrons on each of these species with the carbon atom. So we would end up with either the carbon bonded to the nitrogens here or the oxygens here. And what this means is we can end up with a variety of different products. If we do this reaction with water, we end up with a OH group attacked, and we have a carboxylic acid. If we do this reaction with an alcohol, then we end up attaching an OR group, and we form an ester. If we do this reaction with an ammonia molecule, we end up with NH2 attached, and we end up with an amide. And finally, if we do this with an amine reaction, we end up with NHR, and this is an N substituted amide that we form. So we have 4 possible outcomes using just the acyl chloride with 4 different nucleophiles. Because the acyl chloride is so reactive, all of these reactions will go at 25 degrees Celsius, and we just keep the temperature at 25 degrees Celsius or below and react the reactants together. We're now going to have a look at the work of acid anhydrides and how these can be used in a similar way as the acyl chlorides. Acid anhydrides can be formed by reacting 2 carboxylic acids together, like we've got here, and removing water in a dehydration reaction, and we form the RC double bond O, OC double bond O, R. So they're formed by the reaction of 2 carboxylic acids, normally symmetrical, sometimes unsymmetrical. They are industrially favoured over acyl chlorides because the products of the reaction are an carboxylic acid with the acid anhydrides, and these are less corrosive and more easy to deal with than hydrochloric acid or hydrogen chloride that's formed from the reaction when you use acyl chlorides in reactions with other nucleophiles. Along with this, the acid anhydride is also generally cheaper to produce than acyl chlorides, and another addition to a favouring in industrial processes. First of all then, let's have a look at the addition-elimination reaction, and here we're going to use R, C double bond O, OCOR, where R is CH3CH2. So in this case we've got propanoic anhydride, and we're going to react that with the nucleophile of ammonia, NH3. So the first step is for the lone pair of electrons on the nitrogen to attack the delta positive carbon, and those electrons from the double bond oxygen to go onto the oxygen. In this we then form the intermediate with the negative charge on the oxygen and the lone pair of electrons, and again the positive charge on the nucleophile. The lone pair of electrons then bond back in to the carbon double bond oxygen, and we have the leaving group here of the carboxylate ion. This then leaves the proton, or the NH2, still with a proton on the hydrogen. The hydrogen ion donates its electrons back to the nitrogen atom, and we end up with the NH2 bonded to the C double bond O, and we also have on here O, C double bond O, R and RH plus, which join together to form, in this case, propanoic acid, because we said that our R group was CH2, CH3, and up here with our CH2, CH3 for the R group, we end up with propan amide. Notice there's no E there because the N and the A is a consonant followed by a vowel, so no A is required. As we saw with the acyl chlorides then, the acid anhydrides will react with water, with alcohols, with ammonia, and with the amine groups. And once again, it's the lone pair of electrons on these that will be reacting with the carbon R group, and therefore the bond that eventually gets broken is the one between the carbon and the oxygen, and these hydrogens end up forming with the OCOR side, and our lone pairs on our nucleophiles here will end up bonding to the carbon on the carbon double bond oxygen. And so once again what we find is that with water our product becomes a carboxylic acid. If we use an alcohol, we have OR bonded, and so we form the ester. If we have NH2, then we form the amide. And again, if we have the amine, well, we have NH2, sorry, NHR, and we have the N substituted amide form. And so with those, you should now be able to work out all the reactions with the acyl chlorides and the acid anhydrides. Just to recap then, you should now be able to apply IUPAC names for acyl chlorides and acid anhydrides, draw nucleophilic addition elimination mechanisms for acyl chlorides and acid anhydrides, identify the products or reactions for acyl chlorides and acid anhydrides with various nucleophiles such as alcohols, waters, amines and ammonia, and finally recall the reaction condition for reactions with acyl chlorides and acid anhydrides. That's all for now.